In this lecture, we're going to begin our exploration of long-run economic growth. And we're going to look at some key characteristics of economic growth over the very long run. And then we'll start exploring some of the key ideas macroeconomists have developed to try to understand both the reasons for long-run growth and why it is that different countries, different economies have had different experiences in terms of their economic growth. Why is it that some countries have grown fairly steadily over 100, 200, 250 years, whilst other countries have not enjoyed that economic growth? This is actually one of the really big areas in macroeconomics. Indeed, some of the most exciting developments in recent macroeconomics have involved economic growth, though the study of economic growth is probably one of the oldest parts of the entire discipline of economics. What I want to do in this part of our course is introduce you to some of the key basic fundamental ideas that macroeconomists have found useful to improve their understanding of economic growth. But please be aware that there have been a whole lot of exciting recent developments in this area that have enabled us, I think, to have a pretty good understanding of what really matters for economic growth. But these recent developments have all built on the basic fundamental ideas that we'll cover in this course. And I think you'll find that the ideas that we go through in these lectures enable us to get quite a long way to understanding what are the basic fundamental forces responsible for long-run economic growth. So let's begin with a very important observation. And the observation is this: what you're looking at is gross domestic product per capita for the United States. Very long-run data, indeed, going back to the 1870s. Per capita simply means we're looking at the average flow of GDP per person in the economy. And for industrialised countries, the sort of pattern you're seeing here is fairly typical, where there is a tendency over the long run for the flow of GDP per person to grow, but to grow in a particular way. What you're looking at is known as exponential growth. And an economic variable that has this exponential growth characteristic is one that has this curved growth through time. As you can see, it's not smooth. There are periods where here, the Great Depression of the 1930s, where there was a very serious interruption to growth, and in our work on business cycles to come in later lectures, we'll investigate some of the ideas macroeconomists have developed to explain periods like that. And of course, this is an extraordinary period which represents the incredible increase in production and hence GDP that occurred during the wartime years. I just want to talk a little bit about the nature of exponential growth because there's something quite intriguing about what you're seeing here, but it isn't immediately obvious unless we really delve into the very nature of exponential growth. And I'm going to resort to a little bit of mathematics now. Now, you don't need a lot of heavy-duty mathematics to progress in this course, and I'm not expecting you to have a detailed knowledge of the sorts of techniques I'm going to show you. Some of you will, recall what I'm about to show you from your high school maths, but it's not important for you to work through the maths necessarily, as long as you understand the basic idea that I'm going to convey through the use of this mathematical discussion of exponential growth. So let me explain. What we're interested in is this variable here. I'm using y as my notation for gross domestic product, for real gross domestic product. And the subscript t simply means I'm referring to GDP in a particular time period t. So it might be the year 2010, for example. A variable that grows exponentially can be represented using the following formula. The value for GDP in period t can be related to the value of GDP at some initial period, and we'll call that initial period y0. So that might be here, for example, 1870. And the way we represent exponential growth is as follows. We take that initial value for GDP, multiply it by the following, 1 plus, I'm going to use the Greek letter alpha there to represent the economy's annual growth rate. Alpha, for example, might be a number like 0.02, which would represent an annual growth rate of 2% a year. It turns out that's actually a pretty accurate figure for the United States. But alpha, of course, will differ for different countries. So it's a small number, 0.02 would be a typical number. That's the number for the United States. It represents an annual growth in real per capita GDP of 2% a year. Now, the characteristic of a variable that's growing exponentially is that we take that growth rate, we add to it 1, and then we raise it to the power t. So this is a little mathematical representation that corresponds to this exponential growth that we see in the long-run GDP data. As I said previously, alpha, which is the annual growth rate for the United States, is around 2%. In terms of the actual formula, the way we would represent that is alpha equals 0.02. So what's interesting about that? Let's take that exponential growth formula and manipulate it a little bit. So in any period t, given that GDP is growing exponentially, that can be related to its initial value multiplied by 1 plus the growth rate raised to the power t. Now that's true in general. If it's true in period t, it must also be true in the previous period. So if this first equation relates to the year 2010, then in the year 29 we must also be able to write that the value for GDP in that year is also related to whatever its initial value was, again multiplied by 1 plus that growth rate, but now instead of being raised to the value t, because we're talking about the previous period, that is raised to the value t minus 1. All right, so why am I doing that? When working with variables that grow exponentially, it's often useful to transform the variable into natural logs, and ln is the standard mathematical notation to represent natural log. Again, this will be familiar to many of you from your high school mathematics, but if this is not familiar to you, I'm not expecting you to necessarily understand all the details of the mathematics, but we are going to demonstrate a very important point about long-run economic growth that can really only be explained if I go through this maths, but it's really the point we're getting to that I want you to focus on. But we do have a little bit of work to get there. Now, if I take the natural logarithm of the value of GDP in period t, I can write that as follows. It will be equal to the natural logarithm of the initial value of GDP, y0, plus t times by the natural logarithm of 1 plus alpha. Now, this term here, as long as alpha is a small number and our 2% growth rate, or alpha equal to 0.02 would be considered a small number. But it turns out that there's a very convenient mathematical approximation we can make. The natural log of 1 plus a small number turns out to be approximately equal to that small number itself. And if you have a calculator handy, you might want to just punch some numbers in and check that for yourself. Which means we can rewrite this expression as the natural log of the initial value plus t times alpha. Now, I can do exactly the same transformation with the previous value for GDP, which will give me the natural log of the initial value of GDP plus, not t, but t minus 1 now, multiplied by alpha. Now, none of this necessarily looks all that helpful at this stage, but have a look what happens if I do the following. If I take the natural log of the value of GDP in period t and subtract from it the natural log of the value of GDP in the previous period, what I'm actually doing is subtracting those two expressions. When I do that, the initial values drop out, and I'm going to be left with t times alpha minus t times alpha plus alpha. All I've done is taken those two expressions and subtracted the bottom one from the top one. That gives me alpha. So what is this telling me? It's telling me if I take the natural log of GDP and then take the difference between one period and the previous period, that difference gives me the growth rate, alpha. Now, why is that interesting? What you're looking at here now is our graph of per capita GDP, but this time I've taken the logarithm of GDP, the natural logarithm. And you can see that it no longer has that curved exponential shape, but it now looks much more like a straight line. And that's really important. The slope of that straight line is going to equal the growth rate. And apart from some very unusual historical experiences, most notably the Great Depression, the wartime years, and perhaps even the most recent observations associated with the global financial crisis, what you can see is that for the United States, the growth rate of the economy has been fairly constant over this very, very long period of time. For example, over here, the 1960s to the 1980s, when you look at the data as we have in this graph, it doesn't look all that different to what we saw in the 1880s, 1890s, 1900s. And what macroeconomists have concluded from this is that in the study of long-run economic growth, there are some key fundamental long-run forces at work which probably are acting in pretty much the same way in recent periods as they were some 100, 150 years ago. In other words, it might very well be the case that there are truly some key fundamental, deep structural aspects of an industrial economy that are driving economic growth in some very fundamental sense and are doing so in pretty much the same way today as was the case some 100 years ago. Now, obviously, some of the details are going to be quite different. Technology is very different, for example, but you'll actually see that technology itself is one of these really important fundamental structural forces.